A friend sent me this problem. It's from Vietnam's National Math Competition in 2019, question 1. Here's the original in Vietnamese and here's the English translation. Let f be a continuous function from the real number to a positive, such that the limit of fx as x goes to negative infinity and as x goes to positive infinity are both equal to 0. Part A, prove that f has a maximum value in the set of real numbers. Part B, prove that there exist two sequences x sub n and y sub n, where x sub n is less than y sub n for all n 1, 2, 3, 4, 5, 6, such that they converge to the same limit and satisfy the condition that f of x sub n is equal to f of y sub n for all n. I like this problem. It's very realistic. The function is real continuous, and we're looking for maximum. As you will see from the solution, it's also a nice application of several very fundamental concepts in calculus. What's a little curious about this problem, though, is that these national competitions are often used to find students to participate in the national IMO team, the International Math Olympiad. Well, IMO problems tend not to have calculus. So it's a little curious that this is a calculus problem. Anyway, why don't you press pause and try it first, and then I'll solve the problem. All right, first let's strategize. Let's do part A first. We have a continuous function that's defined on the whole real number line, and it's positive, so it's up here somewhere. But the limit as x goes to infinity is 0, and same thing on the left. And I want to prove that it has a maximum value that's global maximum in all of the real numbers. In calculus, there's a theorem called the extreme value theorem that says this. If a function fx is continuous on a closed interval ab, then fx has both a maximum and a minimum value on that interval ab. It sounds like it should apply in this case, kind of, because we have a function that is continuous, and it's continuous throughout the real number line, so it will be continuous in any given closed interval. But the problem is, the maximum that is guaranteed by this theorem is only a maximum in that closed interval. There's no guarantee that it will also be a global maximum. So for example, if I take my AB here and here, then I have this maximum in it. But there's no guarantee that it's global maximum because the global maximum is actually over there and it's not in that interval. My first instinct is fine. Let's make my closed interval really wide. Then somewhere in there, there's a maximum and it'll be global maximum. Good idea, but not complete. Because what if there's like an extra peak outside of this interval? What if no matter how wide I make my interval, there's still another peak outside of it? I try to go out here to capture that, and there's another peak outside of that point. What if I can never go out far enough? Well, that's when I start using this condition. The condition that the limit of f is 0. Here's the definition of limit of f as x goes to infinity. The limit as x goes to the infinity of fx equals to L means that for every epsilon greater than 0, there exists a large number m such that for all x beyond that m, absolute value of fx minus L is less than epsilon, meaning fx and L are very close. So in general, it means that if this is the value L on the y-axis, once x gets past a certain number m, then the graph of f is going to be very close to the value L. You want epsilon to be 0.01, then go out like this far. If you want epsilon to be 0.00001, then go out further. At some point, you will be able to get the graph of f to be very close to the line L. If I take this definition, I change the L to 0, then that means at some point, fx minus 0 will be arbitrarily small. Fx itself is going to be extremely small if it's going to have a limit of 0. That means at some point, I will be able to come out far enough so that f will be smaller than epsilon. No more peaks. At some point, the peaks will have to end. And the same thing's going to happen over here on the left side, on the negative infinity side. So I can call this M2 and I can call this M1. I see my strategy now. My strategy is to use the definition of limit to go out far enough to pick an M2 on the right side and M1 on the left side, so that out there, f is smaller than epsilon. There's an absolute value, but I don't have to worry about it because f is positive. Way out there beyond M2 on the right, f is smaller than epsilon. Also on the left, way out there beyond M1, f is smaller than epsilon. In between M1 and M2, there will be a peak. There will be a maximum. All I need to make sure is this maximum is larger than epsilon, because then this maximum is the maximum between M1 and M2. Great. If I make sure it's greater than epsilon, then it will also be bigger than every x that's outside of M2 and outside of M1. That makes it larger than all the fx's. So how do I make sure that the maximum here is going to be greater than epsilon? Epsilon is a number I can choose because they say for every epsilon. I'll make sure I choose epsilon small enough. Tell you what, I'll just have to make sure that epsilon is smaller than some value, some known value that is in M1, M2. I'll take f of 0. That's convenient. I can take any really. F of 1, f of 1,000, f of negative 96, doesn't matter. But I'm going to take f of 0. I'm going to choose epsilon that's less than this. Let's say epsilon is equal to 1/2 of f of 0. Then all the f's out here are going to be much smaller than f of 0. That also shows that 0 cannot be out here. And then I'm in business. I'm ready to go. Let's write the proof. Let epsilon be equal to f of 0 over 2, which is smaller than f of 0, because f is a positive value function. By the limit as x goes to infinity of fx equals 0, there exists an M2 such that f of x is less than epsilon. Well, we also know that f of x is positive, so 0 less than f of x less than epsilon for all x greater than M2. This also shows M2 is greater than 0, because all the fx is less than f of 0, so 0 cannot be one of it. And I do the same thing on the left. By the limit that x goes to negative infinity of there exists, that's a symbol for there exists, M2 such that 0 less than fx less than epsilon for all x less than m. Oh, sorry, this is M1. M1. So this also shows that M1 has to be less than 0. By the extreme value theorem, there exists a maximum. Let's say f of x naught somewhere in the interval M1, M2. And that implies that f of x naught is at least as large as f of 0. It's largest in that interval. Actually, let's add another one. Since 0 is in the M1, M2 interval, that means f of x naught is greater than or equal to f of 0. And f of 0 is greater than epsilon. That means f of x naught is greater than fx for all x greater than m2, and also greater than fx for all x less than m1. Therefore, fx naught is greater than everything in here by the extreme value theorem. It's greater than everything out here by the fact that it's greater than epsilon. And it's also greater than everything out here by the fact that it's greater than epsilon. So that means it's greater than everything everywhere. It's greater than or equal to for all x. So yeah, in between here is the greatest because you have the extreme value theorem. And on the two ends is greater than epsilon. There we go, QED for part A. Let's now do part B. Strategize. We have a positive valued function. We know it has at least one maximum because of part A. Let's just say that it may have many. So let's say 2. Things going on in between, things going on the left, and then limit at 0, things going on the right, and limit at 0. We want two sequences, xn and yn, where x is to the left of y, but they converge to the same limit, and the x and y have the same vertical position. If they all have the same vertical position, that means they go kind of like up and down together like this. And if they're going to merge to something, I would imagine that they would merge to one of the maximum. Let's say this one. I can have x and y at, let's say, x1 here, y1 here. And if I want them to merge to that maximum, then I probably want them to sort of slowly increase to that maximum. Maybe x2, y2 over here, x3, y3. But once x4 is over there, for example, y has to be on the other side. They cannot be both on the left of the maximum anymore. And x5, 6, 7, and then somehow I squeeze them in infinite. There's a standard trick in doing things infinite, in making sure that things don't stop at a finite number, and that is to cut things in half. When you cut things in half all the time, you're guaranteed to get to the limit, but you never actually land on the limit, so it will be an infinite sequence. So that's a standard trick. Now that I've looked at this part, maybe I should do that from the beginning. Just have all the x's on the left and all the y's on the right. Then the first condition that xn is less than yn is automatically satisfied. Then I'll just scale them up that way. Let's take away all the red stuff and start again. X1 is here, and my y1 is here. And then I go up by half. I'm aiming at this. So x2 is here, y2 is here. Oh, I now have a problem. x3 is here, y3 is here. And if I continue on, then all the y's are going to converge on this max instead of that max. Adjust my strategy again. Instead of starting with the whole graph, I start in the neighborhood of one of the maxes. Start with the interval, some interval AB around only one max. If there are several max, I just pick one and make sure I do my AB that excludes all the ones around it. So for this one, I would, let's say I start here. And it looks like I need to start a little high. Y1 is here, and X1 is over here somewhere. And then I cut in half, and eventually I'll get to this one. So that's the easy situation. The problem is over here, when I have multiple peaks, and I say that I'm going to make sure I select only one peak, that may not be possible. There are graphs such as sine of 1 over x, where the graph oscillates with the same max of y equals 1, oscillates, and there's no way you can get just a single max in there because there are infinitely many maximum that sort of squeeze in together. So this may not be possible. So what happens when it doesn't work? What if I cannot do this? If there are finitely many maximum in my original AB, I can always narrow it down. So the only reason why I would not be able to narrow it down is because there are infinitely many with only finitely many maxes around x naught. X naught is the max I'm aiming at, and there are infinitely many maxes around it. I want my x's to the left, I want my y's to the right, and you know what? I'm just gonna call this x1, I call this y1. And I jump them in, and eventually they will end here. If I keep narrowing down my AB, then eventually, again, I'm probably gonna do it by cutting the distance in half. Then all the x and y are eventually gonna be squeezed into here. What if it's infinite on only one side? So here's my x naught, and it's infinite on this side. But over here, there may be, I don't know, 1, 2, or maybe 0. Well, what I do is I call this y1, y2, and it will get jumped in as I narrow down my A and B. But at some point, I don't have any more maximum, then you know what? I'll just call this my x, xn. The x can just stay there while the y's jump. X will always be less than y, for 1, and they all have the same f value for 2 because they are all equal to the max. I'm going to do 2 cases. One case is that this is possible. I can have an AB with only finitely many maximums in them, then I narrow it down to just 1. Or if it's not possible, then that means every AB that I try will have infinitely many maximums in it. All right, ready for the proof. Proof of part B. By part A, there exists an x naught such that f of x naught is max. Case 1. There is an interval AB such that finitely many maxes are in AB. Actually, AB containing the x naught. Then what we can do is we can narrow down the AB so that it contains just 1. If there are finitely many, this is actually a mathematical property called the well-ordering principle. If there are finitely many values that are ordered, such as real numbers, then there's a smallest one. Set B between x naught and x max. And set A between x naught and previous max. Then the interval AB contains a unique max at x naught. So it looks something like this. Here's A, here's B. without loss of generality, let's say that we have this situation where f of b is greater than or equal to f of a. Then we're going to set y1 is equal to b. And then we're going to set x1 is equal to a value on that side. How do we know that value exists? We're going to have to use a theorem from calculus called the intermediate value theorem. It's actually from algebra. Here's the intermediate value theorem. It says that if f is a continuous function between a and b, then f takes on every value between these two f values. No matter which z you pick in between the two fa and fb, there's a c that has that f value. By the IVT, pick x1 in the interval a comma x naught such that f of x1 is equal to f of y1. That gets me this x1 here and this y1 here. So we have the equal f, and we have x1 is to the left of x naught, and y1 is to the right of x naught, so x1 is less than y1. There's a slight wrinkle here, and that is if either x1 or y1 is actually equal to x naught, like our interval AB actually falls right on x naught. It really shouldn't because of the way we constructed AB, but just to be careful, I'm going to go back here. I'm going to add on an assumption. Assume x naught is not A and x naught is not B. And I'll deal with when x naught is equal to A and B as a separate case. Right, back here. I have my x1, y1. Now repeat. I'm going to iterate this process. Assume that we have xk, yk. They will be on the two sides of x naught like this. Now I'm going to cut this distance in half. Here's fx naught. Here's f of these two guys. I cut it in half by taking the average. Then yk is plus 1 is here and xk plus 1 is here. Set z is equal to f of x naught plus f of xk divided by 2 by the IVT again. I'm going to find x sub k plus 1 in the interval xk x naught and y sub k plus 1 in the interval of x naught yk. Let's call this z sub k, such that f of xk plus 1 is equal to f of yk plus 1 is equal to f of z, k plus 1. K plus 1. Then because x is to the left of x naught, actually I'm going to do it like this. Make it half open. And I know that it's possible because at x naught, f is equal to like the higher number. It's not going to be equal to the average. Xk plus 1 is to the left of x naught, and yk plus 1 is to the right. Xk plus 1 is still less than yk plus 1. And I repeat, and because the f of xn converge to f of x naught, f of yn converge to f of x naught, and this is unique. There's only one such peak. Then therefore, xn converge to x naught, and yn also converge to x naught. QED. I have QED on this situation. Now I have to take care of a couple more cases. Case 1b and case 1c. And that is a is equal to x naught and b is equal to x naught. In this case, I set xn is equal to x naught for all n. In this case, I set yn is equal to x naught for all n. And then do as case 1. All right, so that takes care of like case 1 generally. I'm thinking that 1b and 1c won't happen, but I'm just writing it down anyway, just in case. And now we're going to move on to case 2. And that is not possible to have case 1. That means every interval containing x naught has infinitely many maxes. As soon as we have an interval that has finitely many maxes, we fall back on case 1. So case 2 only applies if no matter what interval you take around x naught, there are infinitely many maximum points in it. That's important because that means we can keep narrowing down and there will always be an infinite number in between. Here's my x naught. And no matter what AB I put around it, I have infinitely many maxima. It could be on both sides or it could be on just one side. A possibility is I have infinite on one side and finitely many on the other side. And we figured out that we're just going to pick a y on the right, a max on the right to be our y, and a max on the left to be our x. We may have to adjust a little bit that if we couldn't find another max on either the left or the right, then that one we're just going to put it right where x naught is. To make sure that x and y converge to x naught, we're just going to narrow down this interval by cutting in half. Let's start with x1 and y1. Not the same as x naught if possible. We know that at least one of x1 and y1 will be not x naught. Because there are infinitely many max, one of them's got to be on one side, either on the x side or on the y side. That's different from x naught. Now let's do the iterative process. Suppose we're at xk, yk. Here's xk, here's yk. They're both at max, and x naught is somewhere in here. What I want is to get to half the distance. So I have a new a, a new b, and then I find my next y in here and my next x in here. We're going to define our new a and b. Let a, let's say sub k plus 1 is equal to, cut in half the distance between xk and x naught by taking the average, xk plus x naught over 2. Similarly, on the other side, x naught plus yk over 2. Find x sub k plus 1 is equal to a max position in ak plus 1 comma x naught. When I say it's a max, I mean the x value of the maximum f. That's just shorthand. So the longhand is something like x such that f of xk plus 1 is equal to f of x naught. And y sub k plus 1 is a max. That's shorthand for all of this. In x naught, comma bk plus 1. And both of these, we're going to go not equals to x naught if possible. Because there exist infinitely many maxima in each of the a and bn. It's always possible to find one that's not equal to x naught, either on the left or on the right. At least one of xk plus 1 comma yk plus 1 is not equal to x naught. And therefore, we have the required condition that says xk plus 1 is strictly less than y sub k plus 1. And the f value for them both equals to f of x naught because we were intentionally selecting the maxima, and the a and b n converge to just the point x naught. Therefore, x sub n also converge to x naught and y sub n also converge to x naught. All conditions are satisfied. QED. Hope that's been fun. Thanks for watching. Please press like and subscribe for more contents. Bye.